which is opposite direction of the external electric field. So my total electric field has dropped. So my total electric field is the external electric field minus, well, I guess technically you're adding, but it's in the opposite direction, plus the dielectric electric field. Which would just be my external magnitude minus my dielectric magnitude. So we've got a couple other equations here for the parallel plate capacitor. I know that if the electric field is constant in space, so then my change in potential is equal to negative E dot X RS. We also have that the electric field from the plates, this is total electric field, total. The electric field from the plates, magnitude of it is sigma over epsilon, or sigma over kappa, epsilon sub naught. And there's a fifth one I'm working on right now. So we've got the capacitor ones, we got the voltage, the plates. Sigma is Q over A. Well, let's run through this. Take the same setup. I got my 12-volt battery here. I got Q, negative Q. Nothing in between. So kappa is 1. We already found the capacitance. Capacitance is 8.85 nanofarads. What's the charge? Or what's the voltage across? Okay, I guess it should be more specific. Magnitude of it. What is the potential difference between the two plates in our situation here?
12 volts.
Yep, 12 volts. What's the charge on the positive plate? Or how would you find it?
Take the capacitance and multiply by the change in volts.
Let's work on the language. What are you multiplying the charge by? Oh, sorry, you're multiplying the capacitance by what? You would have done it correctly, it's just that the wording was off.
Change in voltage.
It's not changing voltage.
Okay.
Even if I used that expression, and it's possible I had, it is not changing voltage.
You would just multiply the capacitance by
Change in
Yeah, or just voltage. All right, so if I multiply those together, what do I get?
Now 6.2 coulombs, 106.2 coulombs.
Not coulombs.
1.062 times 10 to the negative 7 coulombs.
Quite possibly, yeah. The nanocoulombs or 1.062 times 10 to the negative 7 coulombs. All right. All right, so now we know the charge on the plates. What's the electric field coming from the plates? In other words, that external electric field. Or how would you find it? I guess we could do, oh, we did not give a same distance over there.
0.1 meters. Did you use the ED equation or whatever?
Okay, if you use the ED equation, we're working with the total electric field. So what's the total electric field?
The voltage over the distance.
Okay, therefore,
12. Or the 120
120 what?
newtons per coulomb.
Or volts per meter. All right, so we got 120, and what about from the plates themselves? Hint, there's no dielectric.
Just 120 again?
Yeah. Wait, yeah, 120. Now, we could have done it the other way. Using sigma over kappa epsilon naught, so we have 1.062 times 10 to the negative 7 coulombs divided by 100 square meters. That's sigma over kappa, which is 1, epsilon naught 8.85 times 10 to the negative 12 coulomb squared per meter squared. And ultimately, you're left with newtons per coulomb. And it should come out to 120. If it doesn't, there's a mistake somewhere. Questions? Suppose I want to double my capacitance. What could I do to double my capacitance?
Half your voltage.
If I cut my voltage in half, my charge is going to be cut in half, so that's not going to affect the capacitance.
Make them closer.
All right, we can affect D. Capacitance, especially with the parallel plate capacitor, it's the geometry of the situation. But if I move them to half the distance, so 5 centimeters away from each other, kept everything else the same, my capacitance would double. So I can get a greater capacitance just by getting them really close to each other. But the trouble of getting really close to each other is that you don't want them touching. So the dielectric does two things. One, it throws in a kappa, other than 1, and it allows the two conductors to get closer to each other without touching. All right, so if I move them closer together, as is, What's gonna change here? If I cut D in half, so we said this would double. So this would be 2 times what I originally started with. Call that Q0, call that delta V0, call that E0. So my capacitance has doubled. Is anything gonna stay the same?
No.
The voltage?
Why would the voltage stay the same?
Because of that Kirchhoff rule.
Yeah. So this becomes the same. Voltage will stay the same. So this is another rule to keep in mind, and it's all based on Kirchhoff. If battery connected in a simple circuit, delta V stays the same. All right, so my voltage stays the same, my capacitance doubles, so what else? What's gonna happen to the charge?
Will it double as well?
It should. Because looking at this equation over here, my denominator stays the same, but my left-hand side doubles, the Q has to double. Now my electric field, what's gonna happen to my electric field? If I double the charge? I'm willing to bet at least one of you's got a gut feeling here. Go for it.
It'll become half,
Why half?
because it's voltage is divided by the distance. Or no, the distance is being halved, so never mind, it doubled.
It would double. And there's no dielectric. And you could also have approached it from this point of view here. If Q's doubled, sigma doubles. Bottom stays the same, and so the electric field from the plates would double. And because there's no dielectric, that's the same as the total. All right. I'm now going to disconnect the battery. So this was halving the distance, half D, so done. So now let's disconnect. What changes if I disconnect the battery?
Voltage.
How? We initially found the voltage because of the battery. It was hooked up to it, the battery was connected, so the voltage across here had to be the same as here, plus or minus, depending on which way you were going. But if we disconnect the battery, we could also have found voltage, I'm sorry, do it this way. I could have also realized that my voltage is Q divided by C. Charge divided by the capacitance. The capacitance here is dependent upon the geometry of it. So, will my capacitance change if I disconnect the battery?
No.
So if capacitance stays the same, I guess it's a question of, does my charge change? And if the charge changes, where does the charge go or come from? What's gonna happen to the charge if I disconnect the battery? Assume no humidity in the air, I'm dealing with that. It's not summertime in Columbia, South Carolina.
So it'll stay the same.
It will stay the same, which is another rule we can add to our list here. If the battery is disconnected, charge stays the same. So disconnecting it does not change the charge, so it's still 2 Q sub naught because it was doubled before. My voltage, my capacitance doesn't change, so that's still 2 C sub 0. My voltage doesn't change. What about my electric fields?
They're dependent on the voltage, so I guess they'd stay the same as well.
This was dependent upon the voltage, that's dependent upon the charge, but yeah, they'll both stay. All right, so disconnecting the battery doesn't do anything. What it does affect is what happens next. If I kept the battery connected, so we start out with the initial situation, I move the plates to half the initial distance, and we get these changes. If I don't disconnect the battery, if I move the plates back out to where they were, everything goes back to the original. But if I disconnect the battery and then move them out, so now I separate them back to the original distance, that is going to give us a different result because Q is now fixed. So what's going to happen here is that, so we disconnected, half the distance, disconnect, and then double the distance. 2 times 1/2 P sub naught, or back to the original capacitor. My capacitor goes back to what it was the first time, so that stays the same. My charge stays constant. What happens to the voltage?
Should be half. Or no.
2.
It would double.
Double. Oh, which brings me to the thing I want to talk about. We'll finish this and piece.
How is the voltage related to the charge again?
This relationship here. So Q doubled, C went back to the original, or Q is twice what it originally was, C is back to originally, so this has to be twice what it originally was. My electric fields.
Double.
Double this or double the original?
Double that.
This?
Yes.
So 4 times the original?
Yeah.
Why?
2 times 1/2.
Is 1. The electric field, all right, so totally electric field is this right here. Or, so my voltage is twice what it was. So I've doubled that. My distance is back to what it originally was. I guess looking at the end equation, which is erased. That's doubled. That's the original distance. That would have to be double the original. Which is, so it's double that or equal to that. Another way of looking at it is ultimately the charge was doubled. And if the charge doubles, the charge distribution doubles. Surface charge density doubles, I should say. And therefore the plates would not change from the second situation. All right, so the order in which we do things can affect it. I want to get back to any questions on this before I talk about the insulators and Mondays? I guess one group had the insulator.
If, it was reconnected without the battery, would the voltage disappear?
Reconnected with the battery?
Without, like
Oh.
shorting it?
If it reconnected with that, so all I did was just take those, cut out the battery and then take the 2 leads and touch them, the charge would go to 0. Because all the charge would, now has a path, so all the electrons would go from one plate around the long way to the positive plate. And the electric field would drop to 0 because there's no charge on the plates anymore. The voltage, just some interesting math stuff here, the capacitance would still be the same because the configuration hasn't changed. So the voltage would have to be 0, so you have capacitance is equal to 0 divided by 0. Which mathematically is offensive, and in physics, it's a constant. So I think that's what would happen. There would no charge, no electric field. All right, so the insulator, I was trying to, the issue I had was the fact that the electric field is the negative gradient of the potential. So if the potential is 0 in that region right there, then the electric field would be 0, but the electric field doesn't have to be 0 through an insulator, as in if I threw a dielectric in there. And so I kept going back and